1 o'clock. We start 1 o'clock sharp again. Thank you very much.
Yes.
Okay, and you can see my slides, right?
Yep.
Okay. So thank you very much, Philip. It's very nice to be here. Thank you very much for the invitation to talk and to share some. So I will mostly share some a recent study that we did specifically on trying to predict metastatic relapse in breast cancer, using a combination of machine learning and mechanistic modeling, which is part of a larger effort of trying to take what's best to take from statistics, mathematical modeling, and completely agnostic machine learning. So so you mentioned in your introduction that I am from INRIA Bordeaux, which is true. I mean, was true until very recently, where I have just started a new group. Oops. Do you see my slide?
Yeah.
Do you see the second slide, or
yeah,
are you still? Yeah. Okay. So it's part of a new group called COMPO, which stands for Computational Pharmacology and Clinical Oncology, and which is I'm quite happy that we have been able to gather all these people and to have this team, which is made of people with a mathematical background working in collaboration. I mean, we have in the same unit pharmacologists, both experimental pharmacologists and clinical pharmacologists, and clinical oncologists. So the main focus of the team is working on clinical oncology problems. And yeah, so that's now my new position, and we're trying to combine things. This is a bit of my view of the fields, the different fields that use mathematical and computational techniques in oncology as of today. On the very left, there is mathematical oncology, which has existed. I mean, has existed since several decades, although the term itself, mathematical oncology, dates from 2003, and it's mostly can be defined as defining theoretical models that would be able to explain and reproduce complex behaviors from models that should rely on some basic laws. They are often dynamic models, and we have, I mean, at least in my opinion, we have witnessed quite a lot of success of this type of models, especially models such as branching processes and for evolutionary dynamics and explaining topics about resistance to therapy, for instance. There are also continuous models or deterministic models of tumor growth, including spatial tumor growth. But some limitations of these models, at least in my point of view, is that there are so far been a very limited clinical application or clinical translation of these models. And this comes in part because these models are, at least until quite recently, have been only seldomly validated or confronted to empirical data, even only experimental data, or even less clinical data. And another topic that I want to mention here is that a lot of models are focusing on tumors or on cells or interactions between cells, but very few models are at the level of the organism, at the level of population of tumors, in other words, metastasis. However, in the clinical setting, it's often it's often the relevant case, because especially when we are thinking of systemic therapies, they are given in the metastatic setting. On the other hand, on the other side of the spectrum, as was expressed already this morning, there are techniques from well, either, so here I have grouped say traditional statistical modeling and machine learning and AI under the term of statistical learning here. Although here in this column, I mostly think of the new applications of algorithms that are specially designed to deal with with high dimensional data sets. So we are able to integrate high dimensional data. And the main difference with these algorithms is that they from the beginning focus on prediction tasks rather than inference. So they are really, and they assume the fact that they want to predict, and that's predictive accuracy that is the purpose. And we have in the field of oncology, we have seen very interesting successes of these approaches for integrating genomic data, and starting in the early 2000s, and now and more recently in radiology and histopathology using imaging data. So these are very interesting results. However, with the focus of clinical oncology, and what I mean here by clinical oncology is how to give treatments, mostly drugs, and what drugs to give, and how to administer them. There have been very limited applications, as has been also mentioned before. There is a lack of interpretability of these models, and so far they are often used for static data, but they don't integrate so much the longitudinal aspect and the dynamics, the kinetics of the processes. Another approach that is often, I think, in my opinion, that is too much ignored in terms of the contributions of mathematical and statistical modeling to the field of medicine and specifically oncology, is pharmacometrics. Pharmacometrics dates back to the 80s, and it's methods in pharmacology, so to describe pharmacokinetics or pharmacodynamics data. They make a heavy use of a particular type of statistical framework that Philip was using in his talk this morning, which is called the mixed effects modeling, and which is particularly well appropriate for modeling population data and taking into account inter-individual variability. It has shown a very large success for applications to the design of clinical trials and drug development. It is very much used in the pharmaceutical industry, for instance. And in the recent years, we have seen the fields giving birth to a more specialized part, which is called the quantitative systems pharmacology, where models become more and more complex because they can be fed with more and more complex data. The limitations of this approach is that so far, although having been used for drug development, for instance, they have a limited use in routine clinical management of patients. The modeling is often quite coarse-grained. What I call coarse-grained here is like is quite gross, and there is a lack of integration of large-scale or large-dimensional data. So in our team, we try to combine these three. I mean, we try to inspire ourselves from these three these three types of approaches of math and stats, and combine it with experimental and clinical therapeutics to try to make advances in clinical oncology. Here today, I will focus on the topic of breast cancer of low breast cancer. The main cause of death is metastasis, and although most of the cases are diagnosed as local or regional, there are still a decent fraction that is that. Can you hear me? Yeah.
Sort of. You're sort of breaking up sometimes. Maybe you can try turning off your video.
Yeah.
Yeah.
Let me try to do that. Yeah, I stopped it. Sorry about that. I hope you can still hear. So as you can see on the plot, there are still quite a large fraction of patients who will survive on the long term. About 30% of patients who will survive, will relapse with metastasis, leading to death of the patients. And so estimation of the metastatic risk at diagnosis is key to be able to personalize the amount of adjuvant therapy that has to be administered to individual patients. For instance, the question would be to be able to reduce the number of chemotherapy cycles for patients with a low risk of relapse. So the objectives of the study was to try to use a mechanistic model to predict metastasis, and to combine with machine learning algorithms to select the features prior to feeding the mechanistic model, and try to benchmark, as Ish was saying in his talk, to benchmark the predictive power of the model, of the mechanistic model, to standard survival methods and other predictive algorithms. So yeah, well, again, the idea here is that when we have a black box model, such as a purely statistic model, such as Cox regression model or machine learning model, then we can integrate the data and have prediction and have a classification, for instance, of patients between a low risk and high risk of relapse. But when we have a mechanistic model that is informed by the data, then we can make as outputs, we can make more interesting, maybe more interesting predictions about the amount. Like here on the top right, you have the predicted amount of metastasis and their sizes at diagnosis, and you can also make simulations of different alternative for treatment that can inform clinical decision. So in our case here, the data set that we had was composed of 642 patients who had not received any adjuvant therapy, which means no systemic therapy given after surgery of their primary breast tumor. And on each of these patients, we had 21 features ranging from classical features in breast cancer, such as the hormone receptor status or Ki67 or HER2, to more let's say less classical biomarkers such as staining for EGFR or CD44. And as outcome, we were interested in predicting the metastatic. We had the information about metastatic relapse, yes or no, and the date of the event. So this is right, and with some censoring aspect of the data. So one thing that we did was to try to use an algorithm called random survival forest, which is an adaptation of the random forests ensemble algorithm to survival data. And we did this. We used this mostly to try to see what was the predictive power that we could obtain, and this was quantified by the C-index, which is the equivalent of the equivalent for predicting survival data to the AUC, to the area under the ROC curve. It's a discrimination metric, and this index was not huge, but it's quite comparable to other studies. And what we did was to increase the number of variables that were included in the model to select the optimal number of variables that were optimal for prediction of the outcome. And basically what we found was that there was an increase of the C-index from 1 to 5 features included in the model, but after 5 features, then the predictive power was even decreasing a bit. So we selected, in the end, we selected the 5 best variables, which should be the 5 highlighted in red here. Here there are 8. I'm sorry about that. This is a mistake. So only the first 5 were included in the model. And what showed up, for instance, as significant was the Ki-67, as expected, the tumor size, age, or other factors such as HER2, which is also a classical factor. These are results of, so the C-index quantifies discrimination of the algorithm, but calibration describes the ability to predict, to accurately predict the survival. And this was found quite okay for this algorithm for 5-year outcome and 10 years outcome. And the finding from this analysis was that when we look at some specific covariates, here the age and EGFR, we found that there was, especially for the age, there was a nonlinear effect of the covariates, and also a finding that were indicative of a non-proportional hazard so suggesting that the Cox proportional hazard regression model might not be appropriate. So then we wanted to try to use some mechanistic modeling of metastasis that I have been involved in developing in the recent, for several years now. And this model is basically is simplifying, extremely simplifying the process, but this is needed because of the amount of data that is available. But this model simplifies metastasis between 2 processes, basically growth and dissemination. And in growth, there is growth of the primary here in blue and growth of the metastases here in orange. And they are both characterized by some growth law, which is the growth rate of some of the tumor, which you find in some ODEs that would govern the time dynamics of of the tumor volume or tumor number of cells. So these are the growth flow, and then there is a dissemination rate, which is assumed here to be proportional to the volume of the primary tumor, and with a coefficient of proportionality that is called mu here. And here in this model, you have two parameters for the growth of the primary tumor, two parameters for the growth of the secondary tumors, so the metastasis, and these may or may not be equal or distinct. So that's one question that we had initially in these models, which was, do metastasis grow as with the same growth rate as the primary, or significantly differently? So I don't enter too much into the details, but there has been this very interesting idea to translate this framework into a PDE model. This idea comes from some Japanese researchers in this paper in 2000, where they proposed to model the size distribution of the metastasis rho of T and V, with rho being the density of metastasis at time T with size V. And when we translate the processes of growth and dissemination in this PDE, then growth becomes a transport term in the differential equation and in the PDE, and the dissemination becomes a boundary condition. And yeah, from this quantity, you can compute the metastatic burden, the total mass, the total number of metastatic cells, if you want. And in the case where you assume here, then this is just reduced to a convolution equation, to a convolution formula, which can be solved easily using a fast Fourier transform algorithm. This model was previously, we confronted it and we somehow validated it on animal data using data sets of clinically relevant mouse models of metastasis that are developed by the Dr. John Ebos in his lab in the Roswell Park Cancer Institute, where he grows primary tumors and then observes using bioluminescence spontaneous metastatic disease mostly in the lungs of mice in a breast model. And this is the results on the breast model. We used the mixed effects framework, where we assume well, here it's normal, but it's actually log normal. There's a log normal distribution of the parameters in the population. And so, as you can see here, we could describe the data both at the population level for both the kinetics of the process and the inter-animal variability. So this is the median of the simulations in the metastatic burden, and the 10th and 90th percentiles of the data. And these are individual simulations in individual animals. And from these, we tested different theories with different values of alpha, with different models for the link between alpha and alpha P and beta P, which are parameters for metastasis and primary. And we concluded that a model with the same growth for the primary tumor and the metastasis was able to describe the data, We also, maybe I'll skip this part. And then we went to try to predict the metastatic recurrence, which was my first objective. So we defined the time to recurrence as the first time where there is a metastatic that becomes visible. we also we adapted the mixed effect framework to also describe the censored data. So we basically define the survival function, and we performed. So once this framework is designed, we used likelihood maximization to estimate the parameters using the SAEM algorithm that is implemented in an OR package called SAEM-IX. And these are the results that we obtained, where when describing the metastasis-free survival, we were able to reproduce the survival curves of the data with the, so this is what has to be understood here, is that this black line here is the simulation of the mechanistic model. So these are the survival times that occur from simulation of the model. The parameters were estimated with good accuracy. RSE means relative standard error here. So there was not very high uncertainty on the parameter estimate. There was good practical identifiability. And when for stratification between by the value of the primary tumor size, you see that we have another prediction of the metastatic risk in large tumors, which might be due to the small number of patients in this group. So this was for the descriptive power of the model of the entire data, but when we want to move towards predictive power of the data, this comes to include the covariates into the model, so to include the features. So this is where in this study, this is where it was useful to have done the feature selection previously, because these estimations are quite heavy to perform, and we could not test all the model structures that were possible. So having isolated only the 5 covariates allowed us to reduce the number of model structures that could be tested here. So we included the covariates in the mixed effects model this way, with a dependency on mu and alpha. But the interesting question here from a biological point of view was that we had then a way to test we had a way to test whether a given covariate had a significant impact on the mu part of the model or on the alpha part or on both. And what we found was that the Ki-67 had a significant impact on alpha, but not on mu. And this was reassuring for the model because the Ki-67 is a marker of proliferation, and this was reassuring to find that Ki-67 was correlating with parameter alpha, which is a parameter of growth in the model. On the other hand, a parameter that was correlated with mu was EGFR, and EGFR is a marker of basalness somehow of the cells, which might indicate which might make sense biologically speaking as well. So we had a C-index that was very comparable to what we had before with the random survival model, so forest model, and calibration curve that was also good. These are individual predictions that can be made. So this is where the mechanistic part of the model is quite interesting, because we can reconstruct the natural history. I mean, so this is a full prediction from just the values of the covariates, the biomarkers at the diagnosis and the primary tumor size. Then there is there is prediction. I mean, there is we only take the covariate part of the mixed effects model to predict the value of the individual parameter, and we run the simulation, and we can infer interesting quantities such as the predicted age of the primary tumor, and also we can make predictions about the number of metastases and their sizes at the time of diagnosis. And here you can see two examples of this. Maybe, yeah, I'll go to the next one. This is another simulation, a movie of one of the patient with the prediction of the history of the disease. So this is one example where the model fails to predict well the data, and this is where we can have some information about what happens at the median value of mu and the large value of mu, where in both cases, what is interesting to see here is that in both cases, what is predicted in terms of metastasis is that nothing is visible, which makes sense because this corresponds to the clinical reality. But of course, these two cases where in one case we have two metastases with small sizes, and in other case, a large metastatic burden would predict a very different therapeutic approach. This is a slide where we performed a validation in a second external data set, where we found also even a better agreement of the model to the data. So we were very happy to see that this data set was not used at all for the development of the model. And what was interesting is that in this data set, we had information on another marker, which is pi1. And this pi1 was found to correlate very highly with mu, in this case, not alpha, which makes sense because pi1 is a marker of the degradation of the matrix ability. And the Cox regression model performed similarly in terms of accuracy, positive predictive value, negative predictive value. Okay, and I will conclude on saying that what we had, so as I was just saying, what we observed in this study, that we had similar predictive performances of the Cox regression, random survival forest, and a novel mechanistic model for pure prediction. We also tested other machine learning algorithms that I didn't show here, but performed similarly. But the interesting thing here was that the mechanistic model could provide biological and clinical insights that the machine learning was not able to give. So for instance, that the Ki-67 correlates with the proliferation rate alpha, and that EGFR correlates with mu. So this is a first attempt. This was a first study that we tried, where we tried this approach, and a lot remains to be done, of course. So we have to refine the model to well-established breast cancer molecular subtypes, investigate possibly other mechanistic processes such as dormancy, but is not included in the model yet, and also extend to other external data sets. Very briefly, I want to mention, because this is about the topic of the workshop here, a project that is ongoing in our team now, that is the Quant project, where we have quite a lot of data, especially longitudinal data in quite high dimension, that we try to integrate using mixed effects modeling and statistical learning and machine learning to reduce the dimension into mechanistic models to predict resistance to immune checkpoint inhibition in the non-small cell lung cancer. And this is to somehow make an advertisement, because on this very project, we have an open postdoc position. So if anybody wants to apply, he or she is welcome to do so. And we also have, so our new team compo is quite young, and we are actively looking for, I mean, we have an open research tenure position in the team. So also feel free to apply if you or feel free to reach me if you're interested. Thank you very much, and I would be very happy to answer questions. I don't know how I am on time or.
You're good. Thanks a lot.
Okay. I'm sorry about the connection issues because.
No, that's fine. That's what happens. So thanks a lot for a very nice talk. Do we have any questions from the audience? Anyone? Okay, I'll start with one question then. So I'm working on a similar project where we're looking at metastasis in breast cancer as well, but we're using the SEER database from the US. So it doesn't have any longitudinal data. It only has data from diagnosis, so far as we know. But anyway, we're thinking about similar things. And one thing we have been thinking about is this detection threshold of metastasis. So do you know how, if it's, or rather two questions. So is it a sort of deterministic detection threshold in the sense that as soon as the metastasis reaches above that, then it's detected, or is it sort of stochastic in the sense that you have a detection probability somehow?
Well, I would say that the most rigorous way to do it is stochastic, because it's definitely well, the metastatic relapse occurs. I mean, clinically, it is detected with a very high variability on what is actually the size of the largest metastasis in the organism of the patients, because it can be because of clinical symptoms. It's most of the time because of clinical symptoms, and patients are probably checked every 6 months or so, or even every year. So if you want to make things, I mean, probably this is, I mean, the most rigorous way would be to have some stochasticity and some error incorporated in this thing. However, this is not what we did here. This is not what we did here because for simplicity, just because as a first approach, we just wanted to try what it was giving. So here we used a threshold that would be 5 millimeters, if I remember well, something like 5 millimeter or 10 millimeters in diameter for a metastatic to become visible. And so this is true when there is a frequent follow-up on patients, because that's what radiologists tell us. But for relapse on a 20 years, you know, on 20, I mean, over years of time frame when patients are not imaged. So that's definitely much more questionable to use this. So that's yeah. In our case, that's an assumption that can definitely be improved.
Yeah, because after 5 years, you typically don't have any follow-up, right? And then they have to present with some symptoms in order to be detected.
Yeah. Yes. I think, yeah. So yes, that's the point. Yeah.
Okay, good. I have one more question also about the dissemination rate. So in our work, we have used a constant dissemination rate, actually, which is independent of tumor size, and it seems to work quite well. I know in the original Iwata model, there's another additional parameter, right, the volume to the power of something that you don't have in your model. So
yeah.
Have you tried different sort of functional forms or?
Okay, so what so here we in the original in the experimental work, we had tried several things. This work, and let me see if so the first thing is that even from detailed data like this, it's not possible to identify both mu and the power, but I would call it like gamma here.
Yeah.
Mu and gamma both are, it's not identifiable. Like, okay, if you have a model with both of them, basically it's not identifiable. So then comes the question. Is it possible with gamma equals 0, as you are saying, with gamma equal to third, or with gamma equal 1? In this work, I would have to go back. It's to be sure, but I think we tried with gamma equals 0, and it was not. I would say that it was not working so much. Okay. On the clinical work, we did not try because we kind of took the my reasoning. It might be wrong, but my reasoning was that it should depend somehow on the size of the primary tumor, because tumor size is, well, I don't know, but because tumor size is, is a known factor of risk of metastatic relapse. I know it could be another, I know it could be not linked to this, but and then if it's linked to tumor size, then let's take it linear, because it's the simplest assumption that we could make, and let's see what it gives with a linear. So that's basically the reasoning that we made, which is much not more, which is again an assumption, and can definitely be tested with other forms.
Yeah. Okay, thanks. Do we have any other questions for Sebastián? No. Well, if not, then let's thank the speaker again. Get some clapping hands. There you go. Thanks.
Thank you.
So the next speaker is Sandy Anderson from Florida, and he has not appeared yet, as far as I can see. And part of the reason for that is that it's 7:45 in the morning in Florida. What do we do? Do we take a break, maybe 5 minutes or so, and then we hope that he shows up, and then otherwise we'll have to figure out what to do. Is that okay, Torbjörn?
Sounds good.
Okay, so
That's okay.
5 minutes. So we'll start 10 to 2 with Sandy's talk. Thanks.
Vad har vi för plan B här nu då?
Plan B är väl kanske att ta diskussionen först.